Howdy, my name is Gregory Wong, and I am a senior material science and engineering student at Texas A&M University. And this summer, I've been participating in the O-REU Student Research Program. My project covers the kinetics of dissolution and growth at water mineral surfaces, and my advisor is Dr. Jeffrey Bullard. So before we move much further, I figured I'd provide some background to the project and project goals just so that it all makes sense. So first off, our overall goal is to be able to model the dissolution of ionically bonded solids in water. And we're doing this to be able to determine the reaction rates for these dissolution reactions. My work this summer has been broken into three major phases, the first of which was to design efficient data processing methods. The second was to adapt our existing model to be able to support ionically bonded materials. And the third phase is to add capabilities to support nucleation to the model, so kind of the reverse reaction of dissolution. Moving on, I'm going to be providing a little bit of background to the kinetic Monte Carlo simulation that we have been using this summer. Monte Carlo methods are a very broad class of algorithms that are about as old as computing itself. They work by incorporating randomness to guide the model to an actual prediction. And then kinetic Monte Carlo simulations specifically incorporate that randomness with energetics in order to describe how a system is going to evolve with time. In general, kinetic Monte Carlo simulations are able to model dynamic evolution at much longer timescales than things like molecular dynamics. This is because KMC simulations describe how entire systems are changing between energetic states compared to monitoring how each individual atom within a system is going to be moving. So this saves a lot of computational overhead, and it allows KMC simulations to range into seconds and milliseconds, up into even things like days, months, and years, compared to the normally seen millisecond and nanosecond for molecular dynamics. And finally, we have been using existing source code developed within the Department of Chemical Engineering here at Texas A&M University, and just modifying that rather than starting from scratch on a new kinetic Monte Carlo model. So this code is initially designed to model the metal-water interface, so a lot of the work down the line that I'll be talking about is actually in adapting that code to be able to function with the ionic solids that we've been modeling. Now on to phase one, which was, again, designing a data processing pipeline. So this was pretty much two major steps. So the first was to develop some Python code that was able to import the data and then quickly produce graphs. And then the use of O-REU, which is some free software that is able to visualize the system as it evolved based off some .xyz files that the system outputs. I spent the first few weeks of the summer doing this, which was really nice because it allowed me to both familiarize myself with kinetic Monte Carlo simulations and our code itself, and also with C++ as a programming language. Basically, all of my programming experience in the past was in Python, so it was good to be able to kind of have time to get up to speed and learn a little bit of C++ in the very beginning. So with the Python code, I was working on importing and graphing data. So I had a few major goals for when I was developing this code. First, it needs to be distributable, so I'm not the only person working on this project, so everyone needs to be able to use this same Python code to import and graph data rapidly. Secondly, I want it to be able to operate regardless of where the output files are, so I didn't want the Python script to actually have to be in the same folder as the output data. And finally, I want it to be easy to look at and use for the other people that I've distributed to within my group. So I found that using a Jupyter notebook was the easiest way to accomplish all of these goals. The code's conveniently segmented into cells within the Jupyter notebook file, and you can see below the implementation of this. So the user first is going to insert the file path to where all of their output is, which will have a standard format for all runs, which ultimately makes this code possible. After the path is inserted, they just go through, decide which functions they're actually going to call, and their data will be graphed below. I wrote many functions that were able to describe the system's state as it evolved, things from surface area of the bulk to its system's temperature and even how charge was changing. But the most important functionality was actually monitoring the number of atoms that were still within the bulk as the bulk crystal was dissolving in water. At the bottom of the slide, you can see a function that does this. So this will describe the number of sodium atoms and then plot that versus time as the model runs, but this wasn't actually the most efficient way to do this. I found that every time we modeled a system with a different composition, I'd actually have to go through and rewrite those functions. It wasn't much work, but it did decrease the usability by others. To solve this, I made a generalized number of atoms function rather than something like number of sodium or number of calcium, and it had a call for an element argument. So this was just supposed to be the chemical symbol for the element passed as a string. I was able to do this because, as I said before, the outputs were standardized. So the only thing that was changing was the name of the output folder going from like sodium to calcium, for example. So if I just had that element's chemical symbol as an argument, I could put that in the code, and then the user would just have to pass that as an argument whenever they do the function call, which you might have noticed earlier when I was showing the Jupyter cell that included all of the function calls. This introduced modularity, allows the code to be more easily distributed and used for a larger number of systems. There's very little I can actually say about O-REU. It's really easy to use and was able to quickly produce the videos that you can see running right now. Each frame, the system loses some atoms until it's gone, which also indicates that our model is running properly. Moving into phase 2, our focus was now on changing the model to where it can generate and dissolve ionic solids. So this required us to first be able to generate a second set of lattice points, which would give us one lattice point set for cations and one for anions. And then also we needed to be able to support non-cubic structures. The first structure that we chose to model was calcium hydroxide, which is an important product that forms during the hydration of cementitious binders. This mineral has a trigonal structure, which results in a hexagon of calcium with interior lattice points occupied by hydroxide ions. So generating this structure will result in both of the two requirements being met. So it just needs to have one set of lattice points for the calcium and one for the hydroxide ions, as well as it being a non-cubic structure. Below you can see the reduced unit cell as well as the Wyckoff positions for the mineral. So the Wyckoff positions are actually going to play a very important role in our ability to develop the structure. This is an example of what the code had existing. So this is how a BCC crystal structure is defined. The important things to take note of are lines 5 and 6, which are the basis atoms. So those are basically just the Wyckoff positions that are going to be occupied by atoms in that lattice. So for BCC, we have the vertices of the cube and then the atom that's in the middle of the cube. And then down below, you can see the lattice vectors, which are used by the model to propagate those basis atoms, generating the rest of the bulk structure. So in our adapted code, we were able to hard code the structure of calcium hydroxide. So to do this, as discussed before, we added a second basis to assign the second species to. So lines 6 and 7 are assigning those two floating interior hydroxide ions, and then on line 17 and 18, the second basis is declared, allowing for the calcium atoms to be placed within the lattice. And then, same as last time, the lattice vectors are used to propagate and construct a full lattice out of these Wyckoff positions. Ultimately, we were able to construct the lattice with the green being calcium and the gray hydroxide, and then this is a complete dissolution run. Phase 3, adapting the model for nucleation, is what I'm working on right now. So in general, our model is set up for diffusion and dissolution, and because of this, atoms are effectively just transformed into water upon dissolving, rather than being released as ions. So currently in our interactions inputs, we are able to change what the atoms become. So we could just set them up to become anions or cations, except that's not actually currently working. So below you can see a partially dissolved lattice where the yellow particles are atoms that have been transformed into H2O. I'm working on this currently, so this is more of my plan to solve it. First, I need to figure out why I can't convert bulk atoms into ions directly, and then after that, I'll be able to add code that moves those dissolved ions off of the surface, allowing the bulk to constantly be in contact with that surface so that dissolution will continue past the first layer. And then finally, an interaction type for nucleation will have to be added to the code. Luckily, I will be able to continue working on this project in the fall semester, so this problem should be solved during that time period. Thanks for taking the time to watch my presentation, and I can't wait to see any comments or feedback. I'd also like to extend a special thank you to Dr. Dimkovich and everyone else who made the O-REU possible. This has been a fantastic summer research program. Thanks, and gig 'em.